Hi, and welcome to Chapter 2. In this first section of Chapter 2, out of 2, we're going to be learning how to put a statistic on a single data point's location relative to other points in a distribution. So let's get started. So here's always nice to have a list of objectives for you to review for tests. These are in each of your chapters at the end of the chapter or even at the end of each section maybe, in your textbook. And if you would like a document that has these pre-printed on it for maybe a checklist when you're studying, you let me know and I'll send you one. Okay, so just to remind you, I will not be reading these slides to you. What I'll be doing is using them to bring up things that you don't get from the book. The typical misunderstandings and struggles that students have, common problems they experience or that they don't pick up on. So to try to head it off so that you don't have those problems, or if you did in your reading pick up a problem, maybe we can stop it now. And then to bring up any AP exam tips relative to this topic. So let's look at percentiles. The first thing that comes to mind about students making errors in this particular topic is that they call this something other than percentile. They forget that ILE on the end of the word and they just say percent or percentage. That's wrong, and you will lose credit for it if you use that word in an FRQ when you mean percentile and you say something else. So make sure that you understand the difference between this word, percentile, and percentage or percent, and don't use them incorrectly. So vocabulary misuse is a common AP exam problem. The other issue on this is that the definition here includes this phrase, the P% of the observations less than it, but not equal to. So let's see how that works in this problem, paying particular attention to the mistake I see all the time, people misunderstanding less than and using it as if it says less than or equal to. So Jenny earned a score of 86 on her test. How did she perform relative to the rest of the class? They were kind enough to give you a stem and leaf plot here. If you have to do your own, would you make certain that the leaves are in numerical order, lowest to highest, before you start counting a data point's position? So you count here, you learn there's 25 data points. Then you notice Jenny's score of 86, and you realize that it is the 22nd data point in the distribution. So it has 21 data points less than it out of 25. So there's where you get your percent. 21 out of 25 is the 84th percentile. And make sure you don't say 22nd out of 25 by counting Jenny's score. Always count the ones less than, okay? All right, so here's another type of graph, building on what we learned in Chapter 1 from a frequency graph and then relative frequency. So frequency is just counts. Relative frequency, relative means, relative to other points, and that's percentages. So cumulative frequency, notice it matches. Here's two counts. So these are presidents' ages when they were inaugurated. Two people were inaugurated from age 40 to 44, same as over here. This one is 7 people from age 45 to 49, and this one's 9. So they're just adding as they go. 2 plus 7 is 9. Cumulative means it's adding up each time. So that by the time we get down here, we should have the total number of data points, which was 44. So there we go. So cumulative means you add as you go, and you have all of the data points included in the bottom category. And then cumulative relative frequency just adds the percents up as we go so that we end at 100%. If you only end at 99.9%, that's fine too. That's usually due to a rounding issue, and that won't get you in trouble if you have to make this sort of graph for a question. And necessarily, the graph just gets higher and higher each time. And this is not so hard to understand, but the problem that students have is when they're asked, they're just given the picture and they're not given the chart, and they're asked a percentile question. So you might be asked if a president was inaugurated at age 60, what percentile is he? And you have to go down to 60 and go up and read the value. And so you need to draw a very straight line straight up. Fortunately, this is exactly one of our dots on the graph. But if they said at 57%, you'd go to 57, or excuse me, at age 57, you'd go to 57 on the x-axis, you'd draw a vertical line straight up, okay? And you try not to get it slanted over to one side or the other because that'll give you a wrong answer. So if you go straight up and then straight over a flat line, you have to read the percentile, which is what these percentages are on the relative part, and the cumulative allows it to be percentiles. So the cumulative relative frequency graph will give you percentiles. And if you need to know how many people were in a particular category, you can take the difference of their percentiles and multiply it by the total number of data points, assuming you've been told that. So that's how you use this graph, and it's a very direct statement of it. It's good to do some sample problems in the homework, though. Okay, a different way to measure a data point's position in a data set is called a z-score. The benefit of a z-score is you're able to compare a score on one test with a score on a different test with perhaps a different number of students taking it or a different grading scale. And let's say you took a test in stat class today, and you also took a test in I don't know, what's a big senior AP course, AP Gov today, and you scored a 92 on your stat test and an 86 on your government test. You want to know which score is better. Well, most people would say, well, 92, obviously. But what if the average of the government tests were lower than the average of the stat test? Then how would you tell which one you did better on relative to your peers? So z-scores can take points from two different distributions and compare them together, okay? Talking about distance above or below the mean, okay? So learning to interpret a z-score is very important here because the formula is easy and that's not the point. The point is to understand how it's used. So this little formula, you take the z-score is what you're trying to calculate. So you take your data point, which is x. You subtract the mean of the data set, which gives you how far the deviation, how far a data point lies from the mean. So if it's positive, it's above the mean. And if it's negative, it's below the mean. So that's your first hint. So if a z-score is positive, you know you did better than the average score. And if a z-score is negative, you did worse than the average score. But then we divide it by standard deviation, which is going to tell us how many standard deviations above or below the mean that a score lies. And there is your interpretation that you can take down word for word. I'll say it again. A z-score tells you how many standard deviations above or below the mean that a data point lies. All right, if you need to stop and rewind a little bit and play that back to get the exact wording, I would do that, okay? So you find the z-score for your stats test, you find the z-score for your government test, and you compare those two numbers, and whichever one's higher is the better relative score, all right? That's what this is about. It's what it means. So make sure when you're learning things, and mathematically they're easy, there's probably some meaning in there that you need to pick up at the same time. Not just the ability to tell me what the z-score is, but to interpret what it means. All right? So we're building on this score that Jenny made of 86. The class mean was an 80. Standard deviation was a little over 6 points. What is her standardized score? So you've heard standardized testing. This is part of what they do. So they take the raw score and convert it using some method. Whether they use z-scores or not is proprietary at the College Board and the other testing organizations. So you don't always know what their standard, what their statistic is that they're using. It's really common to use z-scores. And so notice Jenny's score was 6 points above the mean, but that's not quite one whole standard deviation. That's just 1 percentage point under one standard deviation, but it's positive. So she is 1 standard deviation above the mean. All right, so the z-score is the standardized score. Finally, in this section, we have a situation where sometimes you may have to change your data set, but you don't want to stop and remeasure, and you don't want to take another sample. So if you are, and I like the examples they give, they talk about converting a measure from feet to meters, or some such, maybe going from Celsius to Fahrenheit, and arithmetically what we have to do to a number to convert from one measure to another. You know, if it's linear is what this is concerned with, okay? So linear changes include adding, subtracting, multiplying, and dividing. And so let's say we have to take a data set in terms of feet and convert it to meters. Well, we just multiply it by a number and we get a whole new data set. So here's a summary of the effects, and they divide up the different statistics by what type of statistic it is. So for measures of center and location, remember center is easy, mean and median. Location, quartiles, Q1, Q3, that sort of thing. Percentiles, we just went over. Z-scores. If you convert every data point in a data set to z-scores, okay? So if you add a number to each measure, then it's simply going to add that same number to each of these different statistics and any other measure of center and location that you care to use. If you were to add a number or subtract, by the way, it would not change the shape, okay, or the spread. So how far apart, it doesn't make data more spread out or less spread out. It doesn't change the shape of the data. Those things would include range and interquartile range and standard deviation and any other measure, description of shape or measure of spread that you can name would not be affected simply by adding or subtracting a number. Okay. I love the pictures they give for this. So they did a little experiment here. They asked a group of students to guess the distance across a room, basically. And they gave a guess, and then they figured out, if I believe I remember the details from the question right, that everybody was, I can't remember the exact phrasing of the question, but everybody was on average 13 units off or something like that. And so they took everybody's guess and subtracted 13 from it to figure out everybody's error. All right, so you see the two distributions of the exact same shape, and they haven't been stretched out or squished in, so the shape has not changed, and here's proof of it. However, every data point got 13 points smaller when they went from the guess to the error. So that's a beautiful graphic to help you understand that. And there's the summary statistics down below it. You can see that the mean, we started with a guess of 16.02 and the error is 3.02. The SX, that would be the standard deviation of this sample, didn't change. All of the minimum, Q1, median, Q3, and max, all of those decreased by 13, but the interquartile range stayed the same and the range stayed the same. So there's also numerical evidence that adding or subtracting a value to each member of a data set only changes measures of center and location. Okay. So what about multiplying and dividing? So we consider multiplying to be, or dividing to be multiplying by a reciprocal, just like we consider subtraction to be adding the opposite. So we only have two categories here. But if I am going to convert something and I have to multiply each data point by a number or divide, then what changes? Well, according to our summary here, multiplying and dividing changes measures of center and location by multiplying them or dividing them by that same number, just like in the adding and subtracting. So for all four operations, add, subtract, multiply, divide, measures of center and location get changed in the same way. What's different is what multiplying does to measures of spread. All measures of spread, range and IQR and standard deviation, are multiplied by an absolute value of V, but shape is not affected by multiplication. So notice shape is not affected by any of the operators, add, subtract, multiply, divide. Shape never changes. That's because it's not a number. Shape is symmetrical or skewed left or skewed right or what have you, or approximately symmetric. So shape never changes. So that's a nice always thing to remember. And all four operators, add, subtract, multiply, divide, will change measures of center and location. So those are your always. So it's easy to remember which one. Spread is changed by multiplying and dividing, but not by adding and subtracting. And you're going to have to commit that to memory because that's not on a formula sheet anywhere. Okay, so here's our graphic proof of a data set. Here's a reference. I might have gotten the reference question wrong. This is where they ask students to estimate something in meters, and then they converted it to feet or vice versa. And so we have, they took the error, okay, and so it's a continuation of the last one. They took the error and they multiplied it by 3.28 to get it in feet. You see how it was stretched out much farther? That means the spread is wider by a multiple of 3.28. So the distance, the range, the max value minus the min value times 3.28 is how wide this data set is now. But notice the shape is the same. It's just got a much longer tail, but it's the same proportionally to the range. So you can confirm the change down here, that measures of center and location get multiplied by 3.28, that now measures of spread get multiplied by 3.28. So look at standard deviation. Come on. 7.14 times 3.28, 21.43. Also interquartile range, and range got multiplied by 3.28. The only thing that didn't change, see every number up here changed from one to the next, except for the number of data points, of course. The only thing that didn't change is shape. So that's not represented with a number, but you can see it in the graph. All right, that's what's in this lesson. Thanks for listening.